Hello there, and welcome to the Sleep with Science channel. And tonight, we are not simply going to look up at the stars. Tonight, we are going to travel to one of them. Not just any star. Not the sun that warms your skin in the morning. Not the faint and flickering pinpricks of light you see when you step outside on a clear summer evening and tilt your head back and let the darkness settle over you. Tonight, we are going somewhere else entirely. Somewhere that will make everything you thought you understood about size, about distance, about the sheer scale of existence, dissolve quietly and completely, the way a candle dissolves into a room full of sunlight. Because here is a question that most people never think to ask. Here is something that will stay with you long after your eyes have closed and your breath has grown slow and deep and easy. If our sun, the enormous, roaring, nuclear-burning engine at the center of our solar system, the star so massive that over 1 million Earths could fit inside it, if that sun were suddenly replaced by the largest star ever discovered by human beings, do you know what would happen? Do you know how far that star would reach? How much of our solar system it would simply swallow, silently, completely, without effort, the way an ocean swallows a single drop of rain? The answer, when you truly sit with it, when you let it land not just in your mind but somewhere deeper, somewhere quieter, the answer does something to you. It loosens something. It makes the weight of your day feel very, very small. And that is exactly where we are going tonight. But here is what makes this truly extraordinary. This is not mythology. This is not ancient storytelling passed down around a fire. This is science. This is what real human beings, with real telescopes, trained on a real patch of sky, have actually found floating out there in the darkness. A star so incomprehensibly large that the numbers used to describe it stop feeling like numbers at all. They start feeling like poetry. They start feeling like something your mind reaches for and cannot quite hold, the way you might reach for a dream just as it begins to slip away in the earliest light of morning. And in that reaching, in that beautiful, humbling moment of not quite being able to grasp it, something extraordinary happens. The noise quiets. The lists and the worries and the unfinished things all fall away, one by one, like leaves letting go of a branch in autumn, drifting softly down into the dark, warm earth below. So let your body settle now. Feel the weight of yourself against whatever is beneath you. Feel the rise and fall of your breathing, that ancient, automatic rhythm that has kept you alive every moment of your life without you ever having to ask it to. You don't need to do anything right now. You don't need to hold on to anything. All you need to do is listen and let the universe unfold around you. We begin where all journeys into space must begin, with perspective. Right now, as you lie here, the Earth beneath you is spinning. It is hurtling through space at roughly 67,000 miles per hour, carrying every mountain and every ocean and every sleeping creature on its surface along with it, in a great slow arc around our sun. And our sun, in turn, is drifting through the outer arms of the Milky Way galaxy, our home galaxy, a vast, slowly rotating spiral of somewhere between 200 billion and 400 billion stars, most of which we will never see, never reach, never fully know. 200 billion to 400 billion stars. And yet, even within that almost unimaginable crowd, even within that galactic city of burning light, some stars are different. Some stars are so different, so vastly, staggeringly different from everything around them, that when astronomers first detected them, when the data first came back and the measurements were checked and rechecked and checked again, there was a kind of silence in those rooms. A rare and reverent silence. The kind that only comes when human beings are confronted with something that genuinely, sincerely exceeds the scale of their imagination. This is a story about one of those stars. About what it is, where it lives, and what it means, not just scientifically, but in some quieter, deeper way that has nothing to do with equations. Because there is something about standing, even in imagination, even in the soft and drifting landscape of near sleep, before something this enormous, Something about it that rearranges you from the inside. That reminds you of truths you already know but rarely take the time to feel. The universe is not a backdrop. It is not simply the darkness behind the things that matter. It is the main event. It has been expanding and burning and collapsing and being reborn for nearly 14 billion years, and somewhere out there in a region of the sky that, to the naked eye, looks like nothing at all, just a faint smear of distant light, unremarkable, easy to overlook, there is something waiting. Something that has been burning for hundreds of thousands of years before any human eye existed to look up and wonder. Something so large that our entire solar system, the only home our species has ever known, would fit within it like a whisper lost inside a storm. Let that land for just a moment. Let it settle the way snow settles, not all at once, but gently, layer by layer, each flake finding its place in the stillness. Our entire solar system, every planet, every moon, every comet drifting silently through the frozen dark between worlds, every asteroid tumbling slowly end over end in the long, patient belt between Mars and Jupiter. All of it, the full, breathtaking span from the sun to the outermost edge of the farthest reaches of our cosmic neighborhood, all of it, contained inside this star the way a single breath is contained inside a room. And yet, even as I say that, even as those words move through you and find their quiet place somewhere behind your eyes, somewhere in the soft, loosening space of your thoughts, the star itself does not know we exist. It does not feel our smallness. It does not cast its light in our direction with any intention or awareness. It simply burns. It has always simply burned. Long before the first fish pulled itself onto a muddy shore and took a breath of open air. Long before the first forests grew. Long before the first mountain was pushed upward out of the cooling crust of this young and restless earth. That star was already there, already burning, already enormous, already ancient in ways that make our deepest history feel like the opening syllable of a very, very long story. There is something deeply soothing about that, if you allow yourself to feel it. Something that works on the nervous system in the same quiet way that the sound of rain on a rooftop does, or the slow, rhythmic breath of the ocean drawing itself back across a pebbled shore. The universe does not rush. It does not have appointments. It does not lie awake at night running calculations about tomorrow. It simply proceeds, at its own enormous, unhurried pace, through processes that unfold across timescales so vast that even the word million, even the word billion, begins to feel thin and insufficient, like trying to carry water in your bare hands. And we, you and I, in this quiet moment, in this small and sheltered pocket of existence, we get to witness it. We get to know about it. That is one of the most remarkable things about being a human being alive in this particular century, in this particular era of discovery. The telescopes exist. The mathematics exists. The generations of patient, brilliant, curious people who dedicated their entire lives to understanding the sky above them, they existed, and they did the work, and because of that work, we can lie here in the dark tonight and reach our minds across thousands of light years and actually touch, in some real and meaningful sense, something true about the cosmos. That is not a small thing. That is extraordinary. And tonight, that extraordinary thing has a name. But before we speak that name, before we arrive at the destination of this journey, it is worth traveling the road slowly. It is worth taking the long way, the way that winds through the history of human wonder, through the slow accumulation of everything we have learned about the stars and their sizes and their natures, so that when we finally arrive, when we finally stand before the largest star humanity has ever discovered, we feel the full weight of what that means. So let us begin at the beginning. Or rather, let us begin at the beginning of our understanding. For most of human history, the stars were simply lights. Beautiful, reliable, mysterious lights, scattered across the darkness of the night sky in patterns that our ancestors traced and named and told stories about. The ancient Mesopotamians mapped them. The Egyptians aligned their greatest monuments to them. Greek philosophers argued about what they were made of, whether they were holes in a great celestial sphere, whether they were fires burning at the edge of the world. For thousands of years, the stars were intimate in a way that might seem strange to us now. They were woven into agriculture and navigation and religion and myth. They were the first calendar, the first compass, the first reminder that the world was ordered in ways that exceeded ordinary human understanding. But no one knew how far away they were. No one had any real concept of the distances involved. The sky was a ceiling, not an abyss. It was above, not around. The idea that those faint points of light might themselves be suns, vast, burning engines of nuclear fire, some of them larger than anything the human mind had ever attempted to imagine, that idea was not even a distant speculation for most of our history. It was simply not part of the picture. The picture changed slowly. It always does. Knowledge does not arrive all at once, like a door being thrown open onto a bright room. It seeps in, the way light seeps under a door in the early hours of the morning, first just a thin line, barely visible, easy to miss, and then gradually brightening, gradually spreading, until the shape of things begins to emerge from the dark, and you realize the room is far larger than you thought, the ceiling far higher, the walls much farther apart, and out beyond the window. The world stretches on and on and on, far beyond the edge of what any single morning has ever been able to hold. That is how science works. That is how our understanding of the stars has grown, not in sudden revelations, but in slow, patient accumulations of light. Each generation building on the last. Each question answered giving rise to 3 more questions, deeper and stranger and more beautiful than the one before. And each answer, each genuine discovery, carrying with it that rare and quiet feeling of the floor dropping away beneath your feet, not in fear, but in awe, in that clean, breathtaking, almost physical sensation of realizing that the universe is larger than you thought. Again, always larger than you thought. So let us move gently through that history now. Let it wash over you the way warm water washes over tired hands. There is no hurry. The night is long, and the story is deep, and your only task is to breathe and listen and let the images form behind your eyes like slow, luminous clouds drifting through a moonlit sky. The first real shift came when human beings began to understand that the sun, our sun, the one that rises every morning and fills the sky with gold and warmth and the particular quality of light that makes a late afternoon feel like a memory, when they began to understand that the sun was a star. Not a metaphor, not a symbol, an actual star, the same in fundamental nature as every other point of light scattered across the darkness of the night sky. This was not an easy idea to accept. It required a complete rearrangement of the cosmic furniture. It meant that the night sky, which had always felt like a separate realm from the day, was in fact the same realm. That the stars were not exotic decorations on the ceiling of the world, but suns. Distant suns. Each one burning with its own fire, perhaps warming its own worlds, perhaps casting its own long golden afternoons across its own landscapes that no human eye had ever seen. When you truly feel that, not just understand it intellectually, but feel it, the night sky becomes a different thing entirely. It becomes a neighborhood. An unimaginably vast neighborhood, separated by distances that reduce even light to a slow and patient traveler, but a neighborhood nonetheless. A place where our sun is one resident among hundreds of billions, neither the largest nor the smallest, neither the brightest nor the faintest, just one star among a vast and ancient community of stars, each with its own history, its own character, its own particular way of burning. And stars, it turns out, are not all the same. This seems obvious now, perhaps, but it was a profound discovery when it was first made. Stars come in different colors, different temperatures, different ages, different sizes, and the differences in size, in particular, are so extreme, so far beyond anything in ordinary human experience that they require a kind of deliberate mental slowing down to even begin to approach. Consider our sun for a moment. Hold it gently in your mind. It is, by any earthly measure, incomprehensibly large. Its diameter stretches roughly 860,000 miles across. If you could drive a car at highway speed, never stopping, never slowing, in a perfectly straight line through the center of the sun from one side to the other, that journey would take you well over 100 years. A human lifetime spent driving, sleeping in the car, watching the scenery of superheated plasma and nuclear fire blur past the windows, and still you would be traveling, still the far side would be somewhere ahead of you in the blinding, roaring light. And yet the sun is, in the grand catalogue of stars, decidedly average. It is what astronomers classify as a yellow dwarf star, a classification that carries no insult, simply a description of where it falls on the long and varied spectrum of stellar sizes and temperatures. There are stars smaller than our sun, far smaller, dim and cool and ancient, burning with a slow red patience that will outlast everything we can currently imagine. These are the red dwarfs, the quiet elders of the stellar world, and they are by far the most common type of star in the galaxy. Most of the stars in the Milky Way are smaller than our sun. But then there are the others. The ones at the far end of the spectrum. The ones that make the sun itself seem modest, that make its 860,000-mile diameter seem almost quaint by comparison. These are the giant stars, and then beyond the giants, the supergiants, and then beyond the supergiants, in a category so extreme it required its own name, its own language of scale, the hypergiants. These are the stars that push the known boundaries of what a star can be. They are stellar objects so enormous, so luminous, so utterly beyond ordinary proportion, that studying them requires astronomers to regularly pause and simply sit with the numbers before proceeding. Because the numbers do not behave the way numbers are supposed to behave. They do not feel like measurements. They feel like the opening lines of something ancient and unfinished, a story that the universe began telling long before anyone existed to listen, and that continues even now, in the dark and the silence and the vast indifference of space, with no audience but the stars themselves and the slow wheeling galaxies that surround them on every side like the walls of a room too large to ever fully see. And it is into that story that we are moving now. Slowly, gently, the way a boat moves out from a familiar shore into open water, the dock growing smaller behind you, the horizon growing wider ahead, the feeling of the land releasing you inch by inch until there is nothing in any direction but the vast, breathing, luminous dark. Let your body release a little more right now. Let your shoulders drop. Let your jaw unclench if it has been holding. Let the space behind your eyes soften. You are not going anywhere urgent. You are not needed anywhere. The world will be exactly where you left it when morning comes, and between now and then there is only this, only the quiet, only the dark, only the slow and magnificent unfolding of something true and enormous and strangely, deeply comforting about the nature of the universe you live inside of. Because here is something worth holding on to as we go deeper into this story. Here is something that tends to get lost in the numbers, in the measurements, in the clinical language of scientific papers and astronomical databases. Every single thing we know about these stars, every measurement, every classification, every carefully recorded observation, came from a human being who looked up, who stood outside in the dark, or sat before a screen glowing with data, or pressed an eye to an eyepiece, and felt something. Curiosity. Wonder. That particular species of longing that seems to be built into us at some fundamental level, that makes us point at the sky and ask questions that we have no guarantee of ever being able to answer. That longing is not separate from science. It is the engine of science. It is the reason the telescopes were built and the mathematics was developed and the long, patient decades of observation were endured. And tonight, as you rest, that longing is quietly yours too. You are part of that long human tradition simply by being here, simply by being willing to ask the question, to reach your mind out into the dark and follow the light wherever it leads. And it leads, tonight, toward a star in the constellation Scutum. A small, faint constellation, not one that most people could point to on a clear night, tucked into a region of the sky near the great dense core of the Milky Way, where the stars crowd together so thickly that they form a luminous band visible to the naked eye on a truly dark night, a river of ancient light crossing the sky from horizon to horizon. Scutum sits near that river. And inside that constellation, embedded in one of the richest and most complex regions of our galaxy, surrounded by clouds of gas and dust and the light of countless other stars, there is something waiting. But we will arrive there in time. First, let us understand the road that led us there. Let us understand how astronomers learned to measure the sizes of stars at all, because this is itself a remarkable story. A story about human ingenuity applied to a problem that seems, at first consideration, completely impossible. How do you measure the size of something that is thousands of light years away? Something so distant that the light reaching your eyes right now, the light that entered whatever telescope was pointed at it, left its source before recorded human history began. The star itself is not a disk you can easily see. At those distances, even in the most powerful telescopes, most stars appear as nothing more than points of light. Brilliant, sometimes, or faint, but points nonetheless. Not spheres. Not surfaces you can examine. Just light, arriving after its long journey across the dark, carrying information coded in its wavelength, its brightness, its subtle variations over time. And yet from that light alone, from that ancient, patient, information-rich stream of photons, astronomers have learned to extract measurements of breathtaking precision. The temperature of a star's surface can be read from the color of its light, from the particular wavelengths it emits and absorbs, the way a musical chord can be broken down into its individual notes. And from the temperature, combined with the total luminosity, the total amount of energy the star pours into space in every direction every second, the size can be calculated. Not guessed. Calculated. With mathematics so elegant and so reliable that it feels almost like cheating, like the universe left the answer written in a language we just had to learn to read. This technique, refined over more than a century of careful observation and theoretical development, has allowed astronomers to build a catalog of stars arranged by their sizes, their temperatures, their luminosities, their positions on what is called the Hertzsprung-Russell diagram, a kind of map of stellar life, showing where different types of stars sit in relation to one another, how they are born and how they age and how they eventually, in their own time and in their own way, come to an end. Most stars cluster in a long, diagonal band across that diagram called the main sequence. Our Sun sits comfortably in the middle of that band, neither extreme in any direction, a reliable and middle-aged star doing what middle-aged stars do, burning hydrogen steadily at its core, maintaining its size and temperature with remarkable consistency, day after day, year after year, billion after billion year, the long, slow burn of a star at perfect equilibrium, holding itself together through the ancient and elegant balance of gravity pulling inward and the pressure of nuclear fire pushing outward, a conversation between two enormous forces that has been ongoing since before the first human eye ever turned upward and wondered what those lights in the darkness might be. But the main sequence is not the whole story. It is not even close to the whole story. At the edges of the Hertzsprung-Russell diagram, far from the comfortable middle where our Sun resides, there exist stars that defy easy comprehension. Stars that have left the main sequence behind, or never quite belonged to it in the first place. Stars that have swollen beyond anything our intuitions were designed to accommodate. Stars so vast, so luminous, so cosmically disproportionate to everything we encounter in our daily lives, that the only honest response upon learning of their existence is a kind of reverent silence. These are the giants, the supergiants, and at the furthest edge of that category, the hypergiants, A word that sounds almost childlike in its attempt to describe something that language was never truly built to hold. To understand how a star becomes something so enormous, it helps to understand what happens when the fuel begins to run low. A star like our Sun spends most of its life fusing hydrogen into helium in its core, that long, patient burn we spoke of, that billion-year equilibrium. But hydrogen is not infinite. Slowly, over timescales so vast they resist imagination, the hydrogen in the core is consumed. The helium accumulates. And as the hydrogen runs thin, the core begins to contract under gravity, growing denser and hotter, while the outer layers of the star respond by expanding outward in a dramatic and irrevocable transformation. The star swells. It cools at its surface even as it heats at its heart. It reddens. It grows. What was once a star of modest size becomes something altogether different, a red giant, or, for stars of greater original mass, a red supergiant, an object whose outer envelope may extend hundreds of times beyond where the star's surface once was, a slow and enormous blossoming that takes place over millions of years and yet, measured against a human life, seems like something that must have always been, something ancient and permanent and impossible to have ever been otherwise. The Sun itself will one day follow this path. Roughly 5 billion years from now, as its hydrogen supply dwindles, it will begin to swell outward, its surface expanding past Mercury, past Venus, possibly reaching as far as the orbit of Earth itself, though astronomers debate the exact extent of that expansion, and the truth is that long before the Sun's surface reaches our world, the increase in its luminosity will have already rendered the Earth unrecognizable, a scorched and airless stone with no memory of the life that once flourished here. But the Sun, even in its red giant phase, will be a modest thing by certain comparisons. A middling giant among giants. Because there exist stars that began their lives with far greater mass than our Sun, stars born in the densest and most turbulent regions of star-forming nebulae, that swell to sizes that place them in a category almost entirely their own. These are the red supergiants. And among the red supergiants, there are a small number of objects so extreme in their dimensions that astronomers have had to invent new language just to speak of them with any accuracy. Stars that, were they placed at the center of our solar system, would not merely engulf the inner planets but would extend their surfaces out past Jupiter, past Saturn, perhaps to the very edges of where we send our most distant robotic explorers. The night sky, as it turns out, contains several of these objects visible to the naked eye, ancient light from enormous sources, arriving at our retinas after journeys of hundreds or thousands of years, carrying no knowledge of what the star looks like now, only what it looked like when that light first departed. Betelgeuse, the reddish star at the shoulder of Orion, is one of the most famous of these. A red supergiant so large that measuring it precisely has occupied generations of astronomers and remains, even now, a task complicated by the star's own turbulent, irregular surface, which pulses and heaves like the surface of an ocean in a storm, shedding enormous plumes of gas into the space around it, dimming and brightening on timescales of months and years in patterns that are only partially understood. Betelgeuse has fascinated skywatchers for millennia. Ancient observers noted its distinctive color, its brightness, its place in one of the most recognizable patterns in the sky. Modern astronomers have measured it, modeled it, argued about its distance and its diameter and its eventual fate. In late 2019, it dimmed dramatically enough that popular attention briefly turned toward it, speculation rising that perhaps the star was approaching the end of its long life, perhaps the great explosion that will one day unmake it was imminent. It was not. The dimming had other explanations, a cooling of part of its surface, a cloud of ejected dust obscuring our view, and Betelgeuse recovered, brightening again, continuing its slow and ancient rhythm. But the episode was a reminder of something important, that these enormous stars are not stable in the way our Sun is stable. They are dynamic, restless, almost theatrical in their variability, burning so brightly and living so briefly by stellar standards that they seem perpetually on the edge of something, always approaching some threshold, always hinting at the violence that lives inside them, some catastrophic transformation waiting just beyond the next million years or the next 1,000 or, in astronomical terms, perhaps even sooner than that. And yet, for all its drama, for all its fame, Betelgeuse is not the largest star we know. It is not even close to the largest star we know. It is, in the grand catalogue of stellar enormity, somewhere in the upper reaches of what we might call the familiar, a giant we have come to recognize, a name we have learned to pronounce, a presence in our sky that has become almost comfortable in its immensity. But the universe, as it so often does when we imagine we have found its limits, extends further still. To move beyond Betelgeuse is to move into territory that feels less like astronomy and more like mythology. Stars that carry names less widely known but dimensions more difficult to accept. Stars that exist at the absolute outer boundary of what physics, as we currently understand it, permits. Stars so luminous that the very light they produce pushes against their own outer layers with enough force to threaten their structural integrity, to slowly unbind their surfaces and cast their outer envelopes into the surrounding void in great, slow exhalations of stellar material that blur the boundary between the star itself and the nebula it is in the process of creating. There is a class of stars called luminous blue variables, massive, unstable objects that pulse and erupt on timescales of years and decades, shedding enormous amounts of mass in episodes of violence that can briefly make them among the brightest objects in their entire galaxies. And there are the yellow hypergiants and the red hypergiants, each representing a different phase in the short and spectacular lives of the most massive stars the universe produces. Short, in this context, meaning not billions of years but millions, a few million, sometimes, for the most extreme cases, a number that sounds large until you hold it beside the sun's 10 billion-year lifespan and feel the difference, the way you feel the difference between a candle that burns for a week and one that burns so fiercely it consumes itself in an afternoon. Among all of these extreme objects, all these stellar titans arranged at the far edges of the Hertzsprung-Russell diagram, there is one that has, through the slow accumulation of careful measurement and painstaking observation, risen to the top of the catalogue. One star that, by our best current estimates, holds the distinction of being the largest single stellar object that humanity has yet identified. Not the most massive, not the most luminous, though it ranks extraordinarily high in both of those categories as well, but the largest in terms of pure physical diameter, the greatest volume enclosed within a single stellar surface that our instruments have yet resolved. That star is UY Scuti. It sits in the constellation Scutum, the Shield, a small and relatively obscure constellation in the direction of the center of our galaxy, in that rich and crowded band of the Milky Way where stars are dense and the sky, to those who observe from dark places, becomes almost too full to navigate. UY Scuti is not visible to the naked eye from most locations, and even through a modest telescope it appears as little more than a faint reddish point, unremarkable at first glance, giving no outward impression of what it actually is, which is something almost beyond the reach of ordinary thought. It was first catalogued in the mid-19th century by astronomers at the Bonn Observatory in Germany, who noted it simply as a variable star, a star whose brightness changed over time in a regular and measurable way. It was given a designation, entered into the records, and largely passed into the background of the enormous and growing list of stars that astronomers were mapping across the sky. For decades, it was little more than an entry in a catalogue, a data point, a position, a periodicity. Nothing about its name suggested what later observations would reveal about its nature. It was not until the 20th century, and more precisely not until the refined techniques of modern stellar astronomy were brought to bear upon it, that UY Scuti began to reveal its true character. Observations showed that it was a red supergiant. That much was clear from its color, its spectrum, the way its light broke apart into its component wavelengths and told the story of a cool, enormous, luminous surface far larger than anything in our immediate neighborhood. But determining exactly how large required more than color and spectrum. It required distance. Distance is, as we have already spoken of in these earlier reflections, the central challenge of stellar astronomy. Without knowing how far away a star is, its apparent brightness in our sky tells us very little about its true luminosity, and its apparent size tells us nothing at all about its actual diameter. A star might appear faint because it is intrinsically dim, or because it is very far away. A star might appear small because it is genuinely small, or because it is located at such an enormous remove that even a vast surface subtends only the tiniest angle against the sky, an angle so small that measuring it taxes the very limits of our finest instruments. For UY Scuti, the distance estimates have been revised multiple times as better data became available, and each revision has carried with it a corresponding revision in our understanding of the star's true size. The most careful modern measurements place it at roughly 5,000 to 6,000 light-years from Earth, a distance so vast that the light reaching your eyes when you point a telescope toward its position in scutum left that star before the first human civilization had learned to write, before the wheel had been conceived, before the earliest cities had risen along the banks of ancient rivers. The light you would see is old in a way that quietly rearranges something in the mind, a message from a source so remote that the messenger has been traveling longer than recorded human history, arriving now, in this moment, carrying information about a surface that may have already changed beyond recognition. At that distance, and with the angular diameter measurements obtained through interferometric techniques, those careful, painstaking methods of combining the light from multiple telescopes to simulate the resolving power of an instrument far larger than any single telescope could physically be. Astronomers have calculated that UY Scuti has a radius approximately 1,700 times the radius of our Sun. Some estimates place it slightly lower, around 1,500 solar radii, and some slightly higher, and the uncertainty in those numbers is real and worth holding on to, because honest science always carries its uncertainties openly, never hiding them behind the false confidence of a round number stated without qualification. But even at the lower end of those estimates, the number is extraordinary. 1,500 times the radius of the Sun. Let that settle for a moment, the way a stone settles slowly through still water, finding its depth without hurry. The radius of our Sun is approximately 696,000 kilometers. A number already too large for the human nervous system to truly feel. We can write it, we can say it, but we cannot feel it the way we feel the distance across a room or the length of a long walk on a quiet afternoon. And yet that number, that already incomprehensible radius of our own star, must be multiplied by 1,500 or more to arrive at the radius of UY Scuti. The resulting figure is something above 1 billion kilometers, a radius so large that light itself, traveling at the speed it always travels, would require several hours to cross from one side of this star to the other. Think of that for a moment, if you are still awake enough to think, or let it simply move through you like a slow tide if you are already drifting. Light, which crosses the distance from the Earth to the Moon in just over a second, which travels from the Sun to the Earth in 8 minutes, which would circle our entire planet 7.5 times in a single second, that light, moving at that speed, would need hours to travel from one edge of UY Scuti to the other. Hours of uninterrupted travel at the fastest speed the universe allows, just across one star. If UY Scuti were placed where our Sun is, its surface would extend far beyond the orbit of Jupiter. The 4 inner planets, Mercury, Venus, Earth, Mars, would be entirely subsumed, swallowed within the body of the star, orbiting inside it as they do now around the Sun, except that there would be no orbiting, because they would simply be inside, enveloped in the outer layers of a stellar atmosphere so vast and so extended that the word atmosphere no longer quite captures what it is. Jupiter itself, that enormous planet we sometimes call a failed star, with its swirling storms and its dozens of moons, would also lie within the envelope of UY Scuti's outermost layers. Saturn, with its rings, would be close. The boundary of the star's surface, such as it is, and red supergiants do not have clean, sharp surfaces the way smaller stars do, their outer layers fading gradually into the surrounding space in a way that makes the very concept of a surface somewhat approximate. that boundary would lie somewhere in the region of the outer solar system. And yet, for all this enormity, Scuti is not the most massive star we know. Mass and size, in the stellar world, do not always correspond the way intuition suggests they should. The most massive stars are often not the largest in volume, because extreme mass tends to produce extreme luminosity, and extreme luminosity tends to compress and heat the outer layers of a star rather than allowing them to cool and expand into the enormous, extended envelopes that characterize the red supergiants. The most massive stars we know burn so ferociously that they remain relatively compact, relatively hot, their surfaces blazing blue-white with temperatures that dwarf the comparatively cool, reddish surface of Scuti. Scuti, by contrast, has a surface temperature of only around 3,400 Kelvin, cool, as stars go, which is precisely why it is red. That coolness is part of what allows it to be so large. Its outer layers have expanded and diffused and chilled over the course of its evolution, swelling outward as the star ages and its interior structure shifts, the way a coal that has passed its hottest moment begins to glow more dimly but spreads its warmth over a wider surface. It is a star in a late chapter of its life. A star that has already burned through enormous quantities of its original fuel, that has already passed through earlier phases of its existence and arrived at this enormous, distended, luminous state through a sequence of internal transformations. That took millions of years to unfold and yet, in the context of the universe's own timekeeping, passed like a single breath drawn and released in an otherwise unbroken silence. To understand where Scuti is in its life, it helps to understand something about the lives of massive stars in general, the way they burn, the way they age, the way their interiors reorganize themselves in response to the changing chemistry at their cores. Because stellar evolution, for the most massive stars, is not the long, patient, almost geological process it is for stars like our Sun. It is something faster, something more urgent, something that feels, in the language of human timescales, almost dramatic. A star like our Sun, as we have spoken of, will spend roughly 10 billion years on the main sequence, fusing hydrogen into helium in a slow and steady burn, changing so gradually that a civilization watching from a nearby planet would notice nothing different from one millennium to the next. The Sun is, in this sense, a patient star, a reliable star, a star that does not hurry. But a star born with 20 or 30 or 50 times the mass of our Sun is a fundamentally different kind of object. The greater the mass, the greater the gravitational pressure at the core, and the greater the pressure, the faster the nuclear reactions must proceed in order to maintain the equilibrium that keeps the star from collapsing inward on itself. A star of high mass burns not more efficiently but more frantically, consuming its hydrogen reserves at a rate so much greater than our Sun's that what would take billions of years for a solar mass star is accomplished in only a few millions of years for the most massive ones. This is one of the great ironies of stellar existence. The stars born with the most fuel burn through it the fastest. The stars that seem, by virtue of their mass, most endowed with resources are precisely the ones that exhaust those resources most quickly, living their brilliant, enormous lives in a fraction of the time available to their smaller, more modest cousins. A massive star blazes across the sky of its galaxy like something that cannot help but spend itself entirely, while a small red dwarf star barely worth noting in a catalogue will quietly persist for trillions of years, long after the universe as we currently know it has grown cold and dark and still. Scuti began its life as one of those profligate burners, a star of enormous initial mass, born in the star-forming regions near the center of our galaxy, collapsing out of a dense cloud of gas and dust in an event that would have been, had any eyes existed nearby to witness it, one of the most spectacular sights the galaxy had to offer. A protostellar cloud gathering itself together under gravity, heating as it compressed, until at its center the temperatures and pressures crossed the threshold where hydrogen nuclei began to fuse, and a new light was kindled in the dark. That initial mass, the mass Scuti possessed when it first arrived on the main sequence, when it first began its hydrogen-burning life, is estimated to have been somewhere between 25 and 40 times the mass of our Sun. An enormous beginning. A star born already at the far end of the stellar mass distribution, already one of the more extreme objects in its stellar neighborhood, already burning with a luminosity that would have made it visible across enormous distances. And it burned. Quickly and brilliantly it burned, fusing hydrogen in its core, radiating energy into the surrounding space at a rate our Sun could not approach, living its main sequence life in what amounts to a few million years before the hydrogen at its core grew thin and the first great transformation began. The core contracted. The outer layers responded. And the star that had once been a hot, luminous, blue-white object on the upper main sequence began its long outward expansion, cooling as it spread, reddening as its surface temperature dropped, growing and growing until it arrived at the state in which we observe it now, this vast, cool, luminous, slowly pulsating presence in the direction of Scutum, this red supergiant occupying a volume of space so large that the mind, even after extended contemplation, never quite succeeds in making it feel real. It pulses, Scuti. Like Betelgeuse, like many red supergiants, it is a variable star, its brightness rising and falling over a period of roughly 740 days in a cycle that reflects the slow, deep oscillations moving through its enormous body. These pulsations are not the sharp, precise variations of certain other variable stars. They are irregular, approximate, superimposed with other variations that arise from the turbulent convection occurring across its vast outer layers, enormous cells of rising and falling gas each larger than our entire Sun, churning the surface in slow motion, creating a texture and a restlessness that no smooth, idealized model can fully capture. The surface of Scuti, could you somehow approach it and observe it, would look nothing like the surface of our Sun as seen in careful solar images, that relatively smooth, granulated sphere with its sunspots and prominences and occasional dramatic flares. The surface of Scuti would be something altogether more turbulent, more diffuse, more difficult to define, a churning ocean of fire and gas where the boundary between star and space is not a line but a gradient, a slow dissolving of density into the void, a place where the concept of a surface loses its precise meaning and becomes instead a statistical approximation, a region where photons, born in the nuclear fires far below, finally escape the grip of opacity and begin their long journey outward into the dark. This is what astronomers call the photosphere, the layer from which light most readily escapes, the layer we define as the visible surface of a star. But on Scuti, even this definition carries with it a kind of humility, a recognition that we are imposing human vocabulary onto something that does not care for our categories. The photosphere of Scuti is not a crisp shell. It is an enormous, diffuse, slowly churning region spread across a distance so vast that if you placed yourself at its center, you would have no sense of being inside anything at all. You would simply be surrounded by a dim, reddish glow in every direction, a warmth that pressed against you from all sides, a light that came from nowhere and everywhere simultaneously. Above that photosphere, the atmosphere of Scuti extends even further outward, thinning gradually into the interstellar medium. The distinction between where the star ends and where space begins is, in practice, a matter of convention. The outermost layers of gas are being shed continuously, blown away by the slow but relentless pressure of radiation, lost to the surrounding darkness in what astronomers call a stellar wind, though that word, wind, carries with it too much of the ordinary, too much of an autumn afternoon, to adequately describe what is actually occurring. This is not a wind in any familiar sense. It is a continuous, quiet hemorrhage of material, a losing of mass at a rate our Sun could not approach, the star slowly undoing itself across geological timescales, giving back to the galaxy the material it once gathered. Scuti is estimated to be losing mass at a rate perhaps 10 million times greater than our own Sun. Every year, a significant fraction of a solar mass drifts away from it, joining the clouds of gas and dust that surround it, forming a circumstellar envelope, a cocoon of expelled material that hangs around the star like a memory of its former self, like the slow exhalation of something very large and very old. This envelope is visible in certain wavelengths of light, particularly in the infrared, where the cooled and condensing dust grains glow with a warmth that reveals their presence to telescopes sensitive to those longer waves. It was partly this infrared excess, this glow of expelled dust, that helped astronomers identify UY Scudi's true nature and refine their estimates of its distance and its size. And that question of distance is worth dwelling on for a moment, because it is the foundation upon which everything else rests. To measure the size of something so remote, you must first know with confidence how far away it is. UY Scudi lies somewhere in the vicinity of 9,000 light-years from Earth, deep within the plane of our galaxy, in the direction of the constellation Scudum. The uncertainty in that distance carries with it a corresponding uncertainty in the star's calculated radius. The figure most often cited, 1,200 solar radii, perhaps 1,700 at certain estimates, depends sensitively on the parallax measurement and on the corrections astronomers must apply for the dust and gas that lies between us and the star, absorbing and reddening its light, making it appear dimmer and therefore apparently smaller than it truly is. This interstellar extinction, as it is called, is not a trivial correction. The galactic plane through which UY Scudi's light must travel is thick with dust, and that dust scatters and absorbs certain wavelengths preferentially, robbing the light of its blue frequencies and leaving behind a redder, diminished signal. Astronomers must untangle this reddening from the intrinsic redness of the star itself, a red supergiant already burning at only 3,000 to 4,000 degrees Kelvin at its surface, cool by stellar standards, cool enough to allow the formation of molecular compounds in its outer atmosphere, cool enough to glow not white or yellow but a deep, smoldering amber red, the color of embers seen through smoke, the color of something immense and ancient slowly releasing its stored energy back into the universe. It is that color, that particular quality of red, that marks UY Scudi as belonging to a specific and important class of stars, the red supergiants, the largest by volume of any stellar type, the final chapter in the lives of certain massive stars before the end comes, before the interior can no longer sustain the weight above it, before the slow work of gravity finally overcomes the equally slow work of nuclear burning and the star collapses inward in a fraction of a second, releasing in that single catastrophic moment more energy than the sun will radiate across its entire 10 billion-year life. But that ending is not yet. That ending is still perhaps 100,000 years away, perhaps less, a span of time that is both enormously long by human reckoning and astonishingly brief by the standards of stellar evolution, a cosmic eye blink in which UY Scudi continues its slow pulsing, its enormous body rising and falling in those long, irregular rhythms, its surface churning with convective cells that dwarf entire planetary systems, its outer layers bleeding slowly into the surrounding dark, patient and indifferent and vast beyond the reach of ordinary comprehension. There is something particular about the way red supergiants age that deserves a kind of quiet attention, a slowing of thought, a willingness to sit with timescales that refuse to be rushed. The life of a massive star is, in cosmic terms, a brief and extravagant thing. Where our sun will burn steadily for 10 billion years, converting hydrogen to helium in its core with a kind of patient, middle-aged reliability, a star massive enough to become a red supergiant burns through its fuel with a recklessness that is almost difficult to contemplate. The more massive a star, the shorter its life. This is one of the profound and slightly counterintuitive truths of stellar physics, that greatness of scale brings with it a kind of urgency, a compression of destiny, as though the universe exacts a toll on extravagance. A star that begins its life with perhaps 20 or 25 times the mass of our Sun will spend only a few million years on what astronomers call the main sequence, that long stable period of hydrogen burning during which a star exists in a kind of equilibrium, the outward pressure of its nuclear fires balanced against the inward pressure of its own gravity. For our Sun, this equilibrium is a slow and comfortable arrangement, lasting billions of years. For the progenitor of a red supergiant, It is a brief bright morning, a few million years that are almost immediately followed by the dramatic expansion and cooling that transforms the star into the enormous, diffuse, slowly dying thing we recognize as a red supergiant today. During that main sequence phase, the star that would become something like UY Scuti was almost certainly a hot, brilliant blue or blue-white star, a creature of intense ultraviolet radiation and powerful stellar winds, burning so brightly that it would have been visible across enormous distances, a point of fierce light in whatever part of the galaxy it occupied. That original star is gone now, transformed almost beyond recognition into the vast cool ember we observe today. The hydrogen in its core was exhausted, and the core contracted under gravity, heating as it compressed until the temperatures and pressures became sufficient to ignite the burning of helium, and then the outer layers responded by expanding enormously, cooling as they spread outward across space, reddening as their temperature dropped, swelling until the star's radius had grown by hundreds of times. This expansion is not violent. It is not explosive. It happens across timescales of thousands of years, a slow blooming, a gradual unfurling of the outer layers into space while the core continues its increasingly desperate sequence of nuclear reactions, burning heavier and heavier elements in a series of shells surrounding the dense inner regions. Helium burns to carbon and oxygen. Carbon burns to neon and magnesium. Neon and magnesium burn to silicon and sulfur. And silicon burns, in the final stage, to iron. And here the process stops, because iron is the end of the line, the element whose nucleus cannot release energy through fusion, the point at which the star's long nuclear burning finally meets its limit. But that final reckoning is still ahead for UY Scuti. The star is still in the earlier phases of this sequence, still in the red supergiant stage, still burning the products of its original hydrogen fuel in shells and layers, still maintaining, however tenuously, the outward pressure that holds its enormous body against the inward pull of its own mass. And in the meantime, it simply continues, pulsing, shedding material, glowing in that deep amber-red light across 9,000 light-years of intervening space, its light arriving at our telescopes ancient and diminished by the dust it has passed through, carrying within it information that astronomers have learned, painstakingly and over many decades, to read and interpret. The instruments that have observed UY Scuti most carefully are not the kind that gather ordinary visible light. Much of what we know about it comes from infrared observations, from radio telescope studies of the molecular emission lines arising in its cool outer atmosphere, from spectroscopic measurements that reveal the composition of its surface layers and the velocities of the material being expelled from them. Each of these techniques peels back a different layer of the star's complexity, and what they reveal together is a portrait of something enormously dynamic, continuously changing, losing itself slowly to the surrounding medium while maintaining for now the vast scale that makes it so remarkable. To look at an image of UY Scuti in a visible light photograph is, in one sense, underwhelming. It appears as a point of reddish light, barely distinguishable from the many other stars in the crowded field of the galactic plane, perhaps slightly redder, perhaps slightly brighter than average, but not obviously the largest known star in the galaxy. The universe does not annotate itself. It does not place a marker beside the extraordinary to distinguish it from the merely large. The immensity of UY Scuti is something that exists entirely in the mathematics, in the careful analysis of light and distance and temperature, in the slow and painstaking work of astronomers who have spent careers learning to read what the light carries across those enormous distances, translating the faint signals of a dying giant into numbers and models and finally into something approaching understanding, a comprehension that is always partial, always provisional, always subject to revision as new instruments and new techniques bring fresh clarity to old uncertainties. And there is a particular kind of beauty in that provisionality, in the fact that our knowledge of UY Scuti is not fixed and final but alive and evolving, growing more nuanced with each new observation, each new analysis, each recalibration of our instruments and our assumptions. Science, at its most honest, is not a collection of settled answers but a continuous refinement of questions, And nowhere is this more evident than in the study of objects at the extreme edges of what is measurable, objects like UY Scuti, where the uncertainties are not small corrections but significant fractions of the total value, where the difference between 900 and 1700 solar radii is not a minor detail but the difference between impressive and almost incomprehensible. The Gaia Space Observatory, the European mission that has spent years mapping the positions and motions of stars across the galaxy with extraordinary precision, has contributed new parallax measurements that have, in some analyses, suggested a somewhat smaller distance to UY Scuti than earlier estimates, and correspondingly a somewhat smaller radius. These revisions do not diminish the star. They refine our portrait of it. A red supergiant at perhaps 700 or 800 solar radii would still be among the largest known stars in the galaxy, still an object of extraordinary scale, still capable of inspiring the kind of quiet astonishment that we are resting inside now, in this slow and careful exploration of what it means for something to be truly, almost incomprehensibly large. What strikes the mind, when it sits long enough with these numbers, is not only the scale of the star itself but the scale of our ignorance surrounding it. We cannot visit UY Scuti. We cannot send a probe to its vicinity and measure its diameter directly. We cannot stand outside it and observe its pulsations in real time, watching its radius expand and contract over those 740-day cycles with our own eyes. Everything we know comes to us encoded in light, in the particular wavelengths that its surface emits and the ways in which those wavelengths are shifted and altered by distance, by intervening dust, by the motion of the star relative to our own solar system. We are, in a very real sense, reading a letter that was written 9,000 years ago, a letter composed in the language of photons that left the star's surface long before any human civilization had developed written language, before the great cities of the ancient world had risen, before history as we record it had begun. And those photons, having traveled for 9,000 years through the largely empty spaces of the galactic plane, arrive at our telescopes diminished and reddened but still carrying their information, still holding within their frequencies and intensities the signatures of the processes that created them deep in the churning outer layers of a star 1,700 times the width of our Sun. That they carry any information at all across such distances is itself a kind of marvel, a testament to the nature of light as a messenger, patient and tireless, indifferent to the distances it must cross. There is a meditation available here, if you allow yourself to slow toward it. Every star you have ever seen in the night sky is a source of ancient light. The nearest, Proxima Centauri, shows itself as it was 4 years ago. The stars of the Big Dipper as they were between 80 and 120 years past. The Andromeda Galaxy, visible to the naked eye on dark clear nights, as it was 2.5 million years before this moment. And UY Scuti, glowing in the infrared and the deep red of its surface temperature, as it was 9,000 years ago, in the early Neolithic, when human beings were just beginning to settle into agricultural communities, just beginning the long experiment of civilization that would eventually produce the telescopes and the mathematics and the careful reasoning that allows us, now, to know that such a star exists at all. There is something recursive and quietly astonishing in that chain of events. The universe producing, over billions of years, the conditions for carbon-based life. Carbon-based life developing, over millions of years, the neural complexity for abstract reasoning. Abstract reasoning developing, over thousands of years, the tools of science and mathematics. And science and mathematics arriving, finally, at the ability to look back across 9,000 light-years of space and say with reasonable confidence, there is something there, and it is very nearly the largest object of its kind that we have yet found, and we know its radius and its luminosity and its temperature and the period of its pulsations and the rate at which it is losing mass into the surrounding medium, and we know all of this without ever having gone there, without ever having touched it or stood near it, knowing it entirely through the patient interpretation of ancient light. That is what astronomy is, at its deepest level. Not merely the cataloging of distant objects, but the slow recovery of information from across Time and space, the reconstruction of distant realities from the faint signals they send outward in all directions, signals that diminish with distance according to precise mathematical laws but never entirely vanish, carrying always some residue of their origin, some trace of the fires and pressures and temperatures that created them, available to any instrument sensitive enough to receive them and any mind patient enough to interpret what they carry. And the mind, when it is quiet enough, when it has released the urgency of ordinary waking thought and settled into the slower rhythms that this kind of contemplation requires, finds in that interpretation not only information but something closer to wonder, a quality of attention that is different from analysis, that coexists with it but is not reducible to it. You can know the radius of UY Scuti in solar units and still be astonished by it. You can understand the physics of red supergiant evolution and still feel the particular stillness that comes from sitting with the reality that such things exist, that the universe is capable of producing objects on this scale, that the same physical laws that govern the falling of a stone or the burning of a candle scale upward without apparent limit into phenomena so large they resist every attempt at intuitive grasp. This is one of the gifts that astronomy offers, if you approach it in the right spirit. Not merely knowledge, but a recalibration of the sense of scale, a repeated and gentle correction of the tendency the mind has to treat its familiar surroundings as representative of reality in general. We live on a world of a certain size, moving around a star of a certain size, and those sizes become, through long familiarity, the unconscious standard against which everything else is measured. The discovery that there are stars 1,700 times the width of our Sun is not merely an interesting fact. It is a kind of perceptual event, a shift in the internal map we carry of what the universe contains and what is possible within it. UY Scuti participates in this recalibration simply by existing. It does not intend to astonish. It has no awareness of the small, brief creatures on a small, brief world 9,000 light-years away, who have turned their instruments toward it and measured its light and calculated its dimensions with careful and uncertain mathematics. It simply continues, as it has continued for millions of years, burning and pulsing and shedding its outer layers into the surrounding space, following the trajectory that physics laid out for it at the moment of its formation in whatever dense molecular cloud gave rise to it in the early history of this part of the galaxy. That formation event, the collapse of a region of gas and dust under its own gravity, the slow accumulation of material at the center of the collapsing cloud, the gradual heating of that central condensation until the temperatures became sufficient to ignite nuclear fusion, occurred perhaps 8 or 10 million years ago, a span of time that is long by human standards but brief in the life of the galaxy, which has been forming stars for nearly 13 billion years. UY Scuti is, in galactic terms, a young star, a recent development, a newcomer to the stellar population of the Milky Way. And yet, in its few million years of existence, it has already reached the final stages of its evolution, already expanded into the vast red giant form it now occupies, already begun the slow hemorrhage of mass that will continue until the end comes. The region of the galaxy in which UY Scuti resides, in the direction of the constellation Scutum near the inner regions of one of the galaxy's spiral arms, is a place of active star formation, rich in the molecular gas and dust that are the raw materials of new stars. It is a crowded and complex region, thick with interstellar matter, populated by young stellar clusters and the remnants of old ones, crossed by the infrared glow of warm dust heated by nearby stars. In this environment, UY Scuti is not alone in its enormity. There are other large and luminous stars in its general neighborhood, other red supergiants and blue hypergiants and luminous blue variables, a population of massive stars that reflects the richness of the region's star-forming history. But among them, UY Scuti stands as one of the largest in volume, one of the most extended, one of the most extreme examples of what stellar evolution can produce when the initial mass is sufficient and the conditions are right. To exist in that region of the galaxy, embedded in that complex and dusty environment, is to be partly hidden from the universe beyond. The interstellar medium absorbs and scatters the light of UY Scuti, wrapping it in obscuration, making it appear in ordinary photographs as something much less dramatic than it truly is. This hiddenness is itself a kind of lesson about the nature of astronomical knowledge, that the most extraordinary objects are not always the most visible, that the universe conceals as much as it reveals, that the patient work of looking beneath the surface of appearances, correcting for extinction and distance and instrumental limitation, is what separates the catalogue of the obvious from the deeper inventory of what actually exists. And what actually exists, when we turn our full attention toward it, is something that stretches the imagination past its ordinary boundaries, something that refuses to be contained within the comfortable vocabulary of human scale. Consider for a moment what it means to know a star. Not to see it. Seeing is the easiest part, the first and most superficial layer of encounter. To know a star is to peel back its apparent simplicity, to move through the veil of distance and dust and atmospheric distortion until you arrive at something closer to its true nature. UY Scuti has required exactly this kind of patient, methodical unpeeling. Every measurement taken of it has been a correction upon a correction, a refinement of a refinement, as though the star itself were a palimpsest, a document written over and over again by successive generations of instruments and minds, each layer revealing something the previous one had obscured or misread. The first catalogued observation of UY Scuti dates to 1860, recorded by astronomers at the Bonn Observatory in Germany during a systematic survey of the sky. At that time, it was assigned a simple designation, a number, a coordinate, a point of light among thousands of other points of light. Nothing in that early record suggested extraordinary dimensions. It appeared variable, meaning its brightness fluctuated measurably over time, and this variability was noted with the careful neutrality of 19th-century observational astronomy. A variable star. A red giant, perhaps. Something worth watching. And then the watching began, slowly, across generations, without urgency, the way the deepest kinds of understanding always accumulate, not in sudden revelations but in the quiet layering of attention over time. That variability, which those early observers noted almost as an aside, turns out to be one of the most revealing features of UY Scuti's character. It is classified as a semi-regular variable, meaning its brightness changes in patterns that are almost periodic, almost rhythmic, but not quite, like a pulse that hesitates, that skips, that breathes unevenly. The cycle runs to roughly 740 days, a period nearly double the span of 2 Earth years, during which the star expands and contracts in a slow, enormous respiration. The surface heaves outward and then retreats. The luminosity rises and then dims. And in those fluctuations is encoded something intimate about the interior physics of a star near the end of its life. The convective cells churning in its outer layers, the pressure waves moving through plasma too vast to visualize directly, the radiation struggling upward through material that absorbs and re-emits it countless times before it finally escapes into the void. This breathing quality, this pulsation, is common to red supergiants. They are not static objects. They are dynamic, restless, shivering at the edges of their own enormity. The forces holding them together, gravity pulling inward, radiation and thermal pressure pushing outward, have reached an uneasy equilibrium, and that equilibrium is not perfectly stable. It trembles. And in its trembling we can read the interior conditions that no instrument will ever observe directly, because the interior of a star like UY Scuti is sealed behind thousands of solar radii worth of opaque, luminous plasma. We know what happens inside it the same way we know what happens inside the Earth's core, not by going there, but by listening carefully to the vibrations that propagate outward and reach us at last, transformed, carrying their message in a code that patient science can partially decode. There is something consoling about this, if you allow yourself to feel it. The universe does not keep its secrets cheaply or easily, but it does keep them in ways that reward sustained attention. The light that arrives at our telescopes after traveling thousands of light years is not merely illumination. It is information, densely compressed, carrying the fingerprints of temperature and composition and motion and variability and distance. Every photon is a messenger. Every spectrum is a text. And the astronomers who have worked across decades to characterize UY Scuti, who have corrected for interstellar extinction, measured its parallax, analyzed its pulsation period, modeled its atmospheric structure, have been engaged in a kind of reading that borders on the devotional. A slow, careful, reverent reading of light. What that reading has produced, in its most recent and refined iterations, is a portrait of a star whose radius sits somewhere in the range of 1,400 to nearly 2,000 times that of the Sun, depending on the methods used, the assumptions made, the corrections applied. The uncertainty is not a failure of science. It is a testament to how genuinely difficult this kind of knowledge is to extract from a universe that does not label its contents neatly. Even with the instruments of the modern era, space-based astrometry, high-resolution spectroscopy, infrared photometry, UY Scuti remains a subject of ongoing measurement, ongoing refinement, a star whose precise dimensions are still being negotiated between observation and theory. And in the meantime, while that negotiation continues, the star itself goes on existing in complete indifference to the question. It does not wait for us to finalize our measurements. It does not pause its slow pulsation while we correct for the dust that lies between its surface and our instruments. It expands and contracts in its long, drowsy rhythm, shedding material at its outermost envelope where the gravity is weakest and the stellar wind carries mass away into the surrounding nebulosity at a rate that would alarm any human intuition about conservation and permanence. The star is, in a very real and physical sense, dissolving at its edges, losing itself gradually into the space around it, feeding the interstellar medium with the elements forged in its core across billions of years of nuclear burning, returning to the galaxy what the galaxy once lent it in the form of a collapsing cloud of gas and dust long before any human eye existed to witness the transaction. There is a profound circularity in this. The material that makes up UY Scuti, the hydrogen, the helium, the heavier elements synthesized in the crushing pressures of its interior, was not always part of a star. It was once diffuse, spread thin across light years of interstellar space, moving slowly in the cold dark between other stars, caught in the gravitational geometry of a galaxy still arranging itself. Gravity gathered it. Gravity compressed it. And somewhere in that compression, over timescales so long they resist direct comprehension, a threshold was crossed, a temperature and pressure sufficient to ignite nuclear fusion, and a star was born into the darkness. That birth was not an event in the way we usually understand events. It was a process, a gradual brightening, a slow awakening that unfolded across hundreds of thousands of years before anything we would recognize as a stable stellar surface existed. And now, at the far end of that long arc, the star is giving itself back. The stellar wind carries its outermost layers into the space around it continuously, a slow exhalation that has already built up a substantial nebula in the immediate vicinity of UY Scuti, a cocoon of expelled material, glowing faintly in the infrared, a record of the star's ongoing generosity toward the universe that made it. This returned material will cool eventually. It will drift. It will mix with other material in the interstellar medium. And in some distant epoch, measured not in years or centuries but in millions of years, some fraction of it may find itself drawn again into a collapsing cloud, incorporated into a new star or a planetary system, recycled through the vast and patient chemistry of a galaxy that wastes almost nothing. To contemplate this cycle is to feel time in a way that ordinary life does not prepare you for. Human existence is calibrated to decades, to seasons, to the span of a breath and the duration of a night. The cycles that govern the lives of stars like UY Scuti operate on scales that have no natural anchor in human experience. 1,000,000 years is not something we can feel. 1,000,000,000 years is almost entirely abstract. And yet the universe runs on these timescales as naturally as a river runs downhill, indifferent to the brevity of any particular observer standing at its bank, watching the water move. Scuti's eventual fate is written clearly enough in the physics of massive stars, even if the precise timing remains uncertain. Stars of this mass and evolutionary stage are candidates for core collapse, the dramatic, catastrophic endpoint in which the nuclear fuel runs out, the outward pressure fails, and the core implodes in a fraction of a second while the outer layers are expelled in an explosion of almost incomprehensible energy. A supernova. The word is familiar, domesticated by repetition, stripped somewhat of its violence by the casual frequency with which it appears in popular astronomy. But the reality behind the word is staggering. In the moment of core collapse, more energy is released than the Sun will radiate across its entire 10 billion-year lifetime. The star that took millions of years to build is dismantled in a breath, its material flung outward at a significant fraction of the speed of light, seeding the surrounding galaxy with heavy elements forged in the final, frantic moments of nucleosynthesis. What remains after such an explosion depends on the mass of the collapsing core. For stars in certain mass ranges, a neutron star is left behind, an object the size of a city, compressed to densities that make ordinary matter seem almost insubstantial, spinning sometimes hundreds of times per second, radiating in radio waves and X-rays with the regularity of a cosmic clock. For stars more massive still, even that remnant is unstable, and the collapse continues past the neutron star phase into something from which not even light can escape. A black hole forms in the darkness where a star once burned, and the surrounding space reorganizes itself around this new gravity, this new silence. Whether Scuti will leave a neutron star or a black hole behind is a question that current stellar models cannot answer with certainty, because the answer depends on details of the star's mass that remain genuinely uncertain, the same uncertainty that clouds our measurement of its radius, rooted in the same interstellar dust that has complicated every observation made of it from the beginning. The star guards its secrets even in the matter of its own death. And there is something almost elegant about that consistency, that an object so difficult to measure in life would be equally ambiguous about its ending. But the ending, whenever it comes, is not the conclusion of Scuti's significance. The explosion itself will be an event of extraordinary astronomical importance, briefly outshining entire galaxies, visible perhaps across thousands of light-years of space. The material it disperses will enrich the interstellar medium of the Milky Way's inner disk with elements that did not exist in the early universe: carbon, oxygen, silicon, iron, the building blocks of rocky planets and living chemistry. And those elements will travel, slowly, mixed into the great reservoir of galactic gas and dust, available eventually to the next generation of stars and the worlds that form around them, carrying within them the chemical inheritance of a star that burned for millions of years in the dusty interior of the galaxy before any creature on any world had yet learned to look upward and wonder. This is perhaps the most quietly astonishing thing about stars like Scuti, not their size, not their luminosity, not even the drama of their eventual deaths, but the fact that they are laboratories, factories, furnaces operating at temperatures and pressures that no human technology has ever approached, synthesizing elements from simpler ones through processes that took decades of theoretical physics to even partially understand. Every heavy element that exists in the observable universe was forged inside a star. The calcium in bone, the iron in blood, the oxygen drawn in with every slow breath taken in a quiet room at the end of a long day, all of it emerged from stellar interiors, from the same kind of crushing nuclear pressure that defines the core of Scuti at this very moment, across thousands of light-years of distance, in the darkness beyond the visible band of the Milky Way. There is an intimacy in this that astronomy does not always pause long enough to acknowledge. The connection between a star too distant and obscured to see with the naked eye and the body of a person lying still in the dark listening to the night is not metaphorical. It is physical. It is chemical. It is written in the periodic table and in the biology of every organism that has ever drawn breath on this particular world. We are not merely observers of the stellar cycle. We are participants in it, downstream products of it, temporary arrangements of material that pass through the interior of at least one star before arriving here in this particular configuration, in this particular moment, capable of reflection and wonder and the peculiar ache of contemplating distances too large to cross. UY Scuti, in this sense, is not alien. It is ancestral. Its processes are the same processes that produce the atoms of which everything familiar is composed, only operating now on a scale so magnified that the connection becomes difficult to feel directly. The difficulty is one of proportion, not of kind. A star is a nuclear furnace, and so was every stellar predecessor of the atoms in your hand, your breath, the faint sound of wind moving outside a window at night. The universe has only a limited vocabulary of physical processes. It uses them repeatedly, at every scale, from the subatomic to the cosmological, and the same essential story. Gravity collects material, pressure ignites fusion, radiation struggles outward, elements are built and eventually dispersed, plays out across billions of stars in billions of galaxies across the observable cosmos. What makes UY Scuti remarkable within that repeated story is the sheer amplitude of its version of it. Every parameter is pushed toward an extreme. The radius that dwarfs nearly all other known stellar radii. The luminosity that outshines the Sun by a factor of several 100,000. The mass loss rate that exceeds what most stars release across their entire main sequence lifetimes. The pulsation that moves the surface inward and outward over distances larger than the Earth's entire orbit around the Sun. These are not merely large numbers. They represent a physical regime in which the ordinary intuitions about how stars behave begin to strain and occasionally break down, in which the models built on observations of smaller, more tractable stars must be extended and modified and sometimes discarded in favor of frameworks that can accommodate phenomena at this scale. And the models, it must be said honestly, are still catching up. Red supergiants at the upper end of the size distribution remain among the more challenging objects in stellar astrophysics to simulate accurately. The convection that operates in their enormous outer envelopes does not behave the same way convection behaves in smaller stars. The convective cells in a red supergiant can be individually larger than the entire Sun, enormous churning columns of plasma rising and falling in slow, massive cycles that carry energy outward from the interior. These giant convective structures contribute to the surface irregularities that make red supergiants appear mottled and asymmetric when imaged at sufficient resolution, not the smooth, uniform sphere that a simplified model might predict, but something more turbulent, more textured, more alive in its complexity. This asymmetry matters. It means that the concept of a stellar radius, applied to an object like UY Scuti, is itself a simplification. The surface does not sit at a single well-defined distance from the center. It billows. It fluctuates. Different regions of the photosphere exist at different radii simultaneously, separated by distances that would themselves be considered enormous on any human scale. When astronomers report a radius for UY Scuti, they are reporting an average, a statistical summary of a surface that is in constant, slow, massive motion, a boundary that is more like a region than a line, more like a transition than a threshold. This fuzziness, this refusal to be pinned to a single clean number, is characteristic of the universe at its most extreme. Precision is a feature of the middle ranges of physical phenomena. At the edges, at the largest scales and the smallest, at the hottest and the densest, things become probabilistic, gradient, resistant to the neat categories that work well enough in the comfortable middle ground of ordinary experience. UY Scuti exists at one of those edges, in a physical regime where even the question of where the star ends and the surrounding space begins to lose its sharpness, where the stellar wind and the circumstellar envelope and the interstellar medium blend into one another in a gradual, unhurried dissolution that mirrors, in its own way, the larger truth that boundaries in nature are almost always softer than we prefer them to be. We draw lines around things because it helps us think. We say here is where the star ends and here is where space begins. Here is where the atmosphere stops and the vacuum starts. Here is where one era of cosmic history concludes and another opens. But the universe does not particularly honor these lines. It moves through transitions rather than across thresholds. The edge of Uy is not a wall but a gradient, a slow thinning of plasma into something less dense, then less dense still, until the material is too sparse to meaningfully call stellar anymore, and yet it carries the star's chemical signature, its temperature history, the record of its convective activity, outward into the surrounding space. The star is present in that material even after the material has technically left the star. The boundary is permeable in both directions, in the way that all meaningful boundaries eventually prove to be. This permeability extends even to the light. The photons that escape from Uy do not leave cleanly. They pass through layers of the star's own expelled atmosphere, through the circumstellar dust and gas that the stellar wind has built up over thousands of years, absorbing and scattering at each encounter, altered in wavelength and direction before they finally achieve the open interstellar space beyond. And then they travel for thousands of years through the interstellar medium of the galaxy's inner disk, encountering further dust, further gas, further opportunity for extinction and reddening, until at last they arrive at the instruments we have pointed toward that region of the sky, already transformed by the long journey, carrying within their shifted wavelengths the history of everything they pass through on the way. That the light arrives at all is worth pausing on. Thousands of light years of intervening material, and still the photons come. Attenuated, reddened, reduced in number from what set out, but present. Measurable. Interpretable. The universe is not perfectly opaque, even at its most obscured. Something always gets through. And what gets through, received carefully and analyzed patiently, is enough to measure a distance, estimate a temperature, calculate a luminosity, model a radius, construct an understanding that is incomplete but not false, approximate but not arbitrary. Science operates in this space between perfect knowledge and total ignorance, building the best available picture from the light that manages to survive the journey. There is something deeply human about that practice, something that connects the astronomer correcting for interstellar extinction to every other person who has ever tried to understand something partially hidden, something separated by distance or time or the accumulated obscuration of intervening circumstances. We are all, in our various ways, trying to read signals that have been altered by the medium they pass through. We are all correcting for noise and distance and the distortions introduced by the instruments we use, including the instrument of our own perception. The methods of astronomy are a formalization of something more fundamental, the universal project of trying to see clearly in conditions that conspire against clarity. Uy, specifically because it is so difficult to observe cleanly, has become a kind of test of that project's limits and possibilities. Each successive measurement campaign has brought different tools to bear: ground-based optical photometry, near-infrared surveys, space-based parallax measurements from the Hipparcos and Gaia missions, spectroscopic analysis of its atmospheric absorption lines. Each approach has its own strengths and its own systematic uncertainties, and the results they produce do not always agree perfectly with one another. The radius estimates that different groups of astronomers have published over the years span a range wide enough to contain the entire orbit of the Earth around the Sun several times over. This is not a scandal. It is the expected behavior of a measurement problem of this difficulty, and it is being progressively constrained as instruments improve and methods are refined and the understanding of interstellar extinction along the specific line of sight to Uy becomes more precise. What has emerged from this ongoing process of refinement is not a single agreed number but a probability distribution, a range of values within which the true radius almost certainly falls, with some values more likely than others, with the extremes of the range increasingly disfavored as the data accumulates. The star is very probably among the largest known. It may be the largest. The uncertainty about whether it holds that title absolutely does not diminish its extraordinary physical reality. An object that is almost certainly more than 1,000 solar radii in size, whatever the precise number within that regime, is an object that has already exceeded the capacity of direct human intuition to accommodate it. The difference between 1,400 and 1,700 solar radii is, from the perspective of felt experience, essentially nothing. Both numbers point toward the same overwhelming conclusion, that there exist in this galaxy objects so large that our most superlative language reaches its limit before the description does. And in that reaching, in that encounter with the limits of language and intuition both, something valuable happens. The mind that has genuinely attempted to hold the scale of Uy Scuti, that has sat with the numbers and followed their implications and allowed the imagery of comparison to work its slow effect, is not the same mind it was before the attempt. Something has shifted in the internal sense of proportion. The universe has expanded slightly inside it, the way a room seems larger after you have spent a long time sitting quietly in it, attending to its dimensions with more care than the first casual glance allowed. This expansion of internal scale is one of the quieter gifts that astronomy offers, and it is available to anyone willing to slow down long enough to receive it. It does not require a telescope or a university education or fluency in the mathematics of stellar astrophysics. It requires only a certain quality of attention, a willingness to sit with numbers that exceed ordinary comprehension and resist the temptation to domesticate them too quickly, to reduce them to something comfortable before they have had the chance to do their work. The discomfort of genuine vastness, held patiently, eventually transforms into something else. Not comfort exactly, but a kind of spaciousness. A loosening of the habitual sense that the world is the size of one's immediate experience of it. Uy Scuti has been doing this work on human imagination since the instruments became sensitive enough to reveal what it actually is. Each generation of astronomers who has turned its attention toward that dusty region of the inner galaxy and coaxed a better measurement from the available light has extended the invitation a little further, opened the door a little wider. And each person who has encountered the results of that work, whether in the pages of an academic journal or in the quiet of a late night, listening to words move slowly through the dark, has had the opportunity to let the scale of the thing settle into them at whatever depth they were willing to allow. What settles, eventually, is not anxiety. The scale of Uy Scuti is not threatening in any practical sense. It is too far away to affect anything in the solar neighborhood. Its eventual supernova, whenever it occurs across the span of the next million years or so, will be a spectacular astronomical event visible perhaps even in daylight from Earth, but at its distance of several thousand light-years it will pose no meaningful danger to life here. It will be a gift of light, briefly, before it fades into the remnant phase, a neutron star or black hole left behind in the dispersing cloud of its own expelled material, a dense and silent memorial to something that was once among the largest objects in the known galaxy. What settles instead of anxiety is proportion, a recalibration, a gentle but persistent reminder that the frame of reference in which human concerns feel absolute and all-consuming is a very small frame, nested inside larger frames that do not share its sense of urgency. This is not nihilism. It is not the cold conclusion that nothing matters because everything is small against the backdrop of a star 2,000 times the size of the Sun. It is something more nuanced than that, something that takes the vastness and uses it not to diminish but to recontextualize. The same universe that contains Uy Scuti also contains the improbable chemistry of living cells, the specific configuration of matter that produces consciousness and curiosity and the desire to look upward at the night sky and ask what is out there. Both things are true simultaneously, and holding both of them at once is closer to wisdom than either one alone. The star burns on in the dusty interior of the galaxy, indifferent to observation, indifferent to the names we have given it and the measurements we have taken and the words that have been spoken about it in the darkness of rooms where people lie still and let their minds move outward past the ceiling, past the atmosphere, past the orbit of the Moon and the outer planets and the heliopause where the solar wind finally yields to the interstellar medium, outward across the thousands of light years of gas and dust and scattered starlight that lie between here and there. It pulsates in its slow, enormous rhythm. It sheds material at its edges. It converts hydrogen and helium into heavier elements in its core with the patient efficiency of a process that has been running for millions of years and will continue until the fuel runs out and the physics change and the long final act begins. We will watch that ending from a great distance, through instruments not yet built, with methods not yet fully developed, perhaps from platforms not yet conceived. Future generations of astronomers will have better parallax measurements, better extinction maps, better atmospheric models, and they will pin down the radius of UY Scuti with a precision that the current data cannot support. They will watch its variability with uninterrupted continuity across decades of observation. They will perhaps detect the subtle precursors that theory predicts should appear in the centuries before a red supergiant undergoes core collapse, the changes in pulsation period, the increased mass loss, the deepening infrared excess. And when the moment comes, they will see it first as a brightening, then as something extraordinary, then as a fading, and then as a remnant embedded in a glowing shell of dispersed material, the signature of an ending that was also, in the grammar of stellar evolution, a beginning. For now, in this moment, in the particular quiet that belongs to the late hours when the world has slowed and the mind drifts between attention and rest, it is enough to know that it is there. Burning. Enormous beyond easy language. Patient in the way that only things measured in millions of years can be patient. A presence in the galaxy so vast that the light it loses each second to the surrounding darkness would outshine entire civilizations, and so distant that it arrives here as nothing more than a faint signal in a careful measurement, a number in a catalogue, a soft and extraordinary fact held lightly in the mind as the mind itself grows quiet, and still, and finally lets go.